Good afternoon. Today we're going to talk about a new software program called Inkjet Recipe Creation. The purpose of this program is to work with flat panels, and the flat panel consists of a large glass plate, and inside the plate you'll see a number of displays. These represent displays that are going to be put onto that plate. The geometry you're looking at right now is an outline of the display, which we want to cover with some sort of protective resist. So what we want to do is create a recipe for the inkjet equipment to know where it needs to put resist and where it doesn't. Well, we could export this as a giant bitmap or something, but that's not really that efficient since these tend to be the same shape and the only difference is where you start your pattern. So the inkjet recipe creation is going to identify these cells and then create a text output that says how far the corner of each cell is from some reference marker. That'll allow the inkjet machine to move to that position and then rasterize and then move to the next position and rasterize and so on. We can also reuse the same bitmap for each of the many masks. We're calling this our cell, and this is our glass frame or canvas. We want to do this inside of AutoCAD and produce both a bitmap for the cell and also the recipe that says where each one of these cells is located. The first thing you'll notice is when I highlight one of the cells, a whole bunch of them get highlighted and you can see they're a block. But we can't use a block directly. We'll have to explode it in order to access the geometries here. When you start the inkjet recipe program, the first thing you can do if you have your cells in blocks is click explode nested blocks, and then if you say yes, it'll do it. So now when I click on this, and all we have are these lines and arcs that form the boundary. Now that's not very good because these are independent lines and arcs, and there's nothing that tells us that these form a closed figure, which is what we need to fill the interior. So the next step will be to use the line linker, and the line linker will ask us to select the lines to be linked. I'm going to do a window selection, and then I'm going to go from there to there. And I'm going to slide up here and do another window from there to there. Now I've successfully selected all of the lines and arcs that I want to be linked into closed boundaries. Hit enter, and it'll ask me for a search radius. Since it knows the data is in millimeters, it's going to pick 0.1 millimeter, and that's acceptable, so I'll just hit enter. It says 90 polygons were created and 0 chains remain. It turns out if you count these, you'll find that there's actually 90 of them total. A chain is anything that's left over that it can't close. Now all of these polygons have been put on a new layer called ACS polys. Now that we've got our polygons, we can define where our alignment mark should be. It's this little tiny guy here in the corner. Let's zoom in there. We're going to snap to the center of that mark. We're going to go to Define Alignment Mark. Ask me for the design units, which are millimeters. And now select the reference point. Well, I want it to snap to that point. I don't want it to depend on how close I can get. So I use the intersection snap option. And now I just come here and you can see when it hits the intersection, it gives me a little X. Okay, and it's telling me exactly where it found it. The next step would be to find all these cells. For this job, I'm going to turn off all the layers except the polys. So we'll come over here to our layer dialog. We'll turn off 0 chains. Now let's go to select master cell. I'm going to select one of my cells as the reference, and then it'll compare all the other cells to determine which are identical to my reference. Here is my master cell. Okay. Now I'm going to go to the next step, which is to find the matching cells. So I'll select objects, and again I want to do a window. When I'm happy with that, I'll click enter, and you see it's computing now. It found 90 cells matching the master cell. It didn't count the master cell twice. That's the total number of cells it found. So we've identified all of these cells as being members of the group, and we want to do two things. One is we want to create the recipe file, and second, we want to create a bitmap. So we go to here and we say export bitmap. We click OK. We're going to call it seal mask. So I'll call it seal mask. It's going to output it as a BIMP. All right, so it's all done. Now I'm going to export the recipe file. I'll call it CAD freeform model.txt. Just click Save. Okay. Now let's look at these two files. Here's our recipe file, and you can see that each cell gets a name. Right now the number is just arbitrary. And then we get the position of the corner of the extents box, X and Y, and we get the cell width and the cell height. And then we point to the bitmap that represents that cell. It's called sealmaskl.bim. And there's a second one, and then so on and so forth. There should be 90 of these. All right, so that's basically telling the inkjet machine where the upper left corner is on all of these cells relative to the alignment mark. Now let's look at the actual BIMP file. I've opened the BIMP file in Photoshop, and I can then look at the image size. It's quite large. We assumed a DPI around 3000. We will provide a control to have the user set the DPI. You can see it's pretty simple. It just has the outline of the box in black, and wherever the outline doesn't cover the bounding box, you'll see just white pixels. If you zoom into this area here, you'll see that there's a tiny little bit of white there, but that was a tiny radius. Now there's other features we'll be putting into the program. We'll be able to enter user parameters and halftone parameters, and we'll be able to export some kind of vector PDF. We'll be implementing that at some point in time. Thank you.